So an interesting phenomenon arises in set theory, and it was discovered by a man named Bertrand Russell. And in fact, it was named after him, and it's called Russell's paradox. Now, Russell's paradox tells us that if we have a set A, and this set is the set of all sets that are not members of themselves or elements of themselves. And this paradox, you have to go out of your way to find it, but it does exist. So set A is a set of all sets that are not members of themselves. And so we have to consider this set specifically to understand how the paradox arises. And so, for example, and I'm going to keep it abstract here at the beginning, and then I'm going to give a couple of examples to help drive the point home, drive the concept home. And so, if you think about it, set A is a set. A is a set. Now the question is set A in fact a member of itself? Is set A, which is the set of all sets that are not members of themselves. So this set A includes elements that are not sets of themselves. So therefore, is set A itself a set that's not a member of itself? Well, yes, it is. It's not. A is not a member of itself. But A is also, if this is the case, if this is true, then this is also true. If the set A is not a member of itself, it is also a member of itself. And so mathematically this is written as A is a member of itself, which implies that A is in fact not a member of itself. And so here is a formulaic or set theory definition of Russell's paradox. And so we will always think about set A as being how we get Russell's paradox. But let's look at some examples of different sets where this is or isn't true. And so let's see if we can construct a set where it is a member of itself. It is a member of itself. You see up here in the definition is not, and this is very important. But let's think of a set B. And set B, imagine, is a door. Inside a door, inside a door, inside a door, forever. And we can represent this mathematically by drawing these brackets, which indicate sets, a couple of dots indicating infinite, and then closing them. So we have a mathematical expression here that shows an infinitely nested door inside a door. And so this is set B. So if we think about this set, is it a set that is not a member of itself? I would say no, actually it is a set of itself. It is, capital B, is a member of set B. The only element is a door, and the door is inside the door. and so we could have B be an element of B. And it's important when we think about this to distinguish between a subset and an element. We are always talking about elements in this case for the paradox. We are not talking about a subset. Because in our example, it could be a subset, but not an element of. And in this case, we have an example of a set that is in fact an element of itself. And so it would not be part of set A. This set B is not an element of A. And so again, if we think about A being the set of all sets that are not members of themselves, A would not include this set, but it would include itself. Again, it would include itself, and therefore it is also not a member of itself if it includes itself. It gets confusing. So let's do one more example. This time, we'll use green. And this time, let's look at two situations. So imagine we have a set C, and set C is all squares in a plane. And set D is everything else, all things not squares in a plane. And if we have these two sets, let's think about our third set, which gives us the Russell paradox. Well, what would it be? How would we define it? It would be defined, we'll call it set E. And set E is the set of all sets that are normal. And you might be thinking, wait, this is different. Well, not exactly. We are going to say all squares in a plane can't be a member of itself. Set C is not a member of itself. You can't have all squares in a plane, the set of all squares in a plane, be a member of all squares in a plane. It could be a subset. That's why it was important to distinguish between element and subset, but it can't be an element. However, for all things not squares in a plane can be an element of itself. So set D can be an element of set D. And so we have two sets, two separate different sets here that have different outcomes. One, it can be an element of the other. And if you think about it, everything could be a subset of everything. Because everything is something. And so something, sorry, I said subset, I'm an element. Everything is something, and so something could be an element of everything. And so that's how we get D to be an element of D. And so remember, we have our set E here, which has the set of all sets that are normal. And so what is normal? Well, I haven't defined it yet. I am defining set C here to be normal. This is a normal set. And then we have set D is going to be abnormal. And so set E will contain set C. Set C will be an element in set E. And set D will not be an element in set E. But because this is normal, E is a normal set that contains all normal sets. So this tells us that E, in fact, is a member of set E. It is a normal set, and so it can E is a normal set, which is a member of the set of all normal sets. And so this also implies that E is not a member of E, because now it no longer is a normal set. It no longer is not a member of itself. It no longer contains just normal sets. It's now abnormal. Set E is now abnormal. You know what? Wrong color. Abnormal. Set E is now abnormal, which implies this. And there you have Russell's paradox. And so to resolve Russell's paradox, by we I mean Zermelo and Fraenkel, devised an axiom, so a postulate or a new foundation for set theory. And this foundation is called the axiom of choice. And what this axiom says, in its simple terms, is that if you have an infinite collection of sets, like set A is a set of sets, an infinite number of them, you cannot just pick one element from that set and make a new set. And so you can't just have A be a member of A. We can't pick out a set and call it a set. It is an element only. And therefore, with that axiom, you no longer get Russell's paradox. And it led to Zermelo's theorem called the well-ordering theorem, and so on. But this just reminds us that if we change the assumptions made a bit, we get completely different results and completely different way of communicating mathematical concepts. And things can get very dicey when we start thinking about infinity. This is really a concept, an issue surrounding infinity. And so we can be very precise and specific in our definitions, in our assumptions that we make, and how we tackle the idea of infinity. And so with that, I will end the video, and I will see you in the next one.